Hello and welcome to our course on scalable data science. Today's lecture is on Bloom filters. I am Anirban and I teach computer science and engineering at IIT Gandhinagar. So, we are still stuck with this problem of querying. We have looked at hash tables, right? But again, let us revisit what we have. We have talked about the problem of building a library where we have a lot of books, but a particular user comes to you, gives you ISBN or a book name and has asked you whether this book is there in your collection, and you are wondering how to answer this question efficiently. You also could be the designer of a network switch, right, which has very limited memory. And now a particular user again comes and asks you, have you seen this IP? Have you seen any traffic for this IP passing through this switch? And you have to answer this question more or less accurately at least. Okay. So, how do we do that? So, let us look at some simple solutions first. So, the solution that we looked at in last class was that of building a hash table. So, just to pin down the notation, we have a universe size U. The cardinality of U is very big, but now we are only looking to store a set of elements n that is much less than the cardinality of U, right? And we said that what if we create a hash table? So, a hash table was of size m, and this m was chosen based on the amount of memory you have access to. But regardless of m, the space, because we use chaining or something similar to that, the space that you need is really n times log of the cardinality of U, right, because each of the elements that you get is going to have an ID and you have to store the ID, and the size of this ID is log of cardinality of U, and you are going to store n of them. Therefore, the total space that you will use is at least n times log of cardinality of U. Your query time, however, is going to depend on your hash table, right? And if you happen to use at least a nice hash function, then your query time can be order n by m. You cannot hope to make it much smaller than this, right? Because it's, I mean, this is average load factor, and most of the, and in expectation every entry of your array m has this much load. Okay. The other extreme is to create a bit array of size cardinality of U. So, here you do not store the element IDs, you know U in advance, and you keep a bit array of the same size of that. And what do? You devote one bit for every element of the universe. So, the space needed is of course just exactly the cardinality of U. However, now you have reduced the query time to be order 1, right. So, there is a trade off. There is a trade off that in creating a hash table, your space is probably quite a bit less, but your query time is a little bit more. In storing a bit array, your space is potentially a lot, but your query time is only order 1. The question is, can we do better than either of them? Okay. So, it turns out that it depends, right. You cannot do better if you are not willing to commit any errors, right. So, let us think about what kind of randomizations and what we did in the hash table construction. In the hash table construction, we did use random hash functions. However, these random hash functions or the algorithms that we created using them never return an incorrect answer, right, because at the end of it we always say yes or no depending on the comparison of the actual element IDs. Okay. So, the query time is a random variable, right, because the query time depends on how sort of uniformly the hash function that you have chosen sprays the elements that are there in the array, right. However, it does not return a incorrect answer ever, and these kinds of randomized algorithms are known as Las Vegas algorithms. The name stems historically. I have no clear, I did not find a clear answer why, but that is what this is called. That is, when you do not return an incorrect answer, but the computational complexity of your algorithm depends on the randomization. The other style of randomized algorithms, and which is what we will look at now, is known as a Monte Carlo randomized algorithm. So, in the Monte Carlo randomized algorithms, we are allowed to return incorrect answers with a small probability, and this probability, let's call it delta, is something that the user will typically define to you, right. So, the user will give you a small probability, a small target error probability delta, and you are allowed to return incorrect answers with this probability delta, and you have to choose the parameters of your algorithm so as to hit this target. Okay. So, here is what we will do. So, the data structure that we will look at to answer the query question is known as a Bloom filter, and this was developed by Butt and Bloom in 1970. So, Bloom filter again is a very simple data structure. There is a bit array, it is basically a bit array, it is a bit array of size m. Okay. But now instead of one hash function, there are k hash functions, h1 to hk. I am not telling you what k is right now, we will get to that a little later. But each hi is a map from every element of the universe to again the indices of the hash function, again the indices of the array 0 to m minus 1. That is, mathematically speaking, each hi is a map from u to 0 to m minus 1, which is what this expression denotes. So, we might use that later on also. Okay. So, intuitively what are we going to do? When an element x arrives, we are going to calculate now h1 of x, h2 of x and h3 of x, in this case k equal to 3, and now we are going to look at these bits, right, b of h1 of x, b of h2 of x and b of h3 of x, and do something with it. So, what do we do with it? Let us see. So, what we do is, when trying to insert an element x, we just turn all these bits from 0 to 1. Okay. That is simple. This is when we are inserting, but what we do when we query, right, that when a query q comes, right, and I calculate, let us say h1 of q, h2 of q and h3 of q, and what do? Do I return yes if only one of them say yes? Do I return yes if a majority of them say yes? Do I return yes if only if all of them say yes? So, it is not clear, and that is what we will and let us try to nail that down. Okay. So, here is basically the entire set of operations you can do with the Bloom filter. So, we will start by initializing b very simply by setting b of I equal to 0 for all the positions. When an element x comes, when we are trying to insert x into the Bloom filter b, we calculate hi of x for I equal to 1 to k, and then we go at all these positions and set all of them to be 1. That is it. Okay. The interesting thing happens, as we saw when we are looking up, that given a particular x, now x is now a query which may or may not have been inserted in the Bloom filter. Now we are trying to say that, now we are trying to answer the question that is x in the set already, has x been added to the Bloom filter yet, right. And in order to do this, here is what you do. You first calculate all the bits, look at all the bits b of hi of x. So, now we have k bits, and we take the AND of these bits. So, we do not look at any one of them, we do not look at the majority of them, we look at their AND of these bits. And if the AND of these bits return present, if the AND of this bits is true, then you return present, and if the AND say is false, then you return absent. Okay. Clear? So, now let us see. Let us try to do some analysis of this. Okay. So, here is a simple enough statement. If the element x has been added to the Bloom filter, then lookup of Bx will always return present. And this is pretty clear, right? Because if the element x has been added to the Bloom filter, then when we are adding it, we have turned on these bits already, and no other addition, no other insertion turns off these bits, because we never turn off bits. So, therefore, these bits once turned on will always remain on, and therefore, lookup of Bx will return present. So, this is fairly clear, right. Now, the interesting thing is the other question. What happens if x has not been added to the filter before? Is it still possible that lookup of Bx will return present? Yes, it is, unfortunately. And here is a simple example. You can probably construct simpler examples though. That suppose we have two elements x and y, right. So, think of the blue arrow as the function h1, think of the red as the function h2, think of the green as the function h3. So, x turned on these 3 bits, y turned on these 3 bits, and now a query comes. Now, it is not very hard to see that if the query is being mapped using h1 to this position, if the query is being mapped using h2 to this position, and using h3 to this position, right. In that case, lookup of this query will return yes, because x and y have turned on these bits. So, this is unfortunate though, but this is what we said, that we can make an error. The only question now is, can we bound the probability of this error? Can we say that the probability of this happening is really small? Okay. So, and this is what we call a false positive, right, that we returned a positive answer, but that is false. So, what are the parameters of the Bloom filter? The parameters, the two parameters that are really at hand are the size of the Bloom filter m and this mysterious number k, which is the number of hash functions. So, just to sort of do a sanity check, recall that if I were just using k equal to 1, that is really just a normal bit array, right, there is nothing interesting there going on. So, what is the effect of changing this k? I mean, k cannot really be decreased to be less than 1, but what really happens when k is increased? So, if you think about it, really two things are happening. Increasing k possibly makes it harder for false positives to happen, right, because lookup, when you call the lookup function, it looks at k bits and takes their AND. So, if k is large, then the chance that any one of these bits has been turned on by some other element is going to decrease as k increases. So, therefore, that is a good thing, right. Therefore, increasing k potentially decreases the chance of false positives to happen, or rather the probability of false positives, it decreases the probability of false positives. However, it is not as straightforward, unfortunately, because if you think about it, if you increase k, then you are filling up more and more of the hash table, more and more of this bit array, right. So, in the extreme case, if k equal to n, if even one element turns on all the bits, right. So, therefore, increasing k is not always good. And then the next question is that is there an optimal way to choose this k, right? Then is there a sweet spot such that if I choose the k according to this particular value, right, that sort of balances out these two effects, that sort of gives me some effect of sort of decreasing the false positives in the lookup, as well as it maybe does not fill up all the entries so fast. So, is there a way to choose k in a smart way, right? So, in order to analyze this, we need to analyze the event of what is happening when we call lookup of Bx, right. So, if x has been inserted, there is nothing much to do, because we know that lookup of Bx will always return present. However, let us look at what happens if x has not been inserted before, but now we are querying it, and so we want to bound the probability that lookup of Bx returns present, because that is the bad event, that is the false positive event. Okay. So, I mean, for this analysis, let us start out by assuming that H1, H2, Hk are all fully independent, are all independent of each other. Okay. We will talk about what happens if they are not completely independent. So, and let us also start out by assuming that probability that for any event that for any of these Hi's, the probability that H of I, that the probability that Hi of x equals j for a fixed j and for a fixed x equals 1 by m for all x and j. That is, all that really says is that given any x, the probability that it maps to a particular, it is equally likely to fall in, it is equally likely to map into any of the positions of the array. Okay, that is all this says. So, under this assumption, when we have inserted n elements, right, suppose we have inserted n elements. So, we have turned on k times n bits, right, because each element insertion turns on k bits. Okay. So, now and these k bits, so for choosing each of these bits has been chosen uniformly among the bits from 0 to m minus 1. So, now let us look at the n the bit hi, the position hi of x. Now, let us look at the position hi of x. Okay. So, what is the probability that this bit is still 0? So, if this bit is still 0, the only way it could happen is that all the k n insertions that have happened until now have happened in the other m minus 1 positions, right. That none of the k n insertions until now have tried to turn this bit to be on, and the probability of that event is 1 minus 1 by m to the power k n, right. And this approximately is e to the power k n by m, and we will use this approximation. We get this because 1 minus 1 by m to the power m, you can write it as approximately e to the power minus 1, and therefore, 1 minus 1 to the power k n is like e to the power k n by m. Right. So, this is a very tight approximation. You can do slightly better analysis than this, but this is what we will stick to. So, now we are saying that the probability of a single bit being 0 is e to the power minus k n by m, right. So, now lookup, when we lookup return present, lookup will return present if all the k bits, h1 of x, h2 of x and until hk of x, all of them say 1, right. So, the probability of that is that each of them are individually 1, and the probability that any one of them is 1 is 1 minus e to the minus k n by m, because the probability that it was 0 was e to the power minus k n by m. So, therefore, the probability that h1 of x, the bit h1 of x is 1 minus e to the minus k n by m. So, therefore, the probability that all these k bits all of them are 1 is nothing but 1 minus e to the minus k n by m to the power k. Okay. So, notice this is not entirely accurate, because it is possible that h1 of x equals h2 of x. However, these are all marginal cases, and but analyzing these marginal cases needs a little more heavyweight machinery that we will not go into. For now, let us just stick to this almost correct analysis. So, now we have the probability of a false positives to be the probability that the lookup of Bx is present, to be this expression 1 minus e to the minus k n by m to the power k, right. So, notice that this expression very nicely captures the two roles of k, right, because as k changes, the inner expression 1 minus e to the minus k n by m increases as changes one way monotonically as k changes, whereas this to the power k definitely decreases. So, the expression inside actually increases, but the expression outside tends to pull k, tends to pull the value of these particular the power of k tends to pull the value down. Okay. So, the question is that is there a sweet spot? Can we choose k to minimize this probability? Okay. So, now it is actually fairly simple. Let us have a shorthand notation. Let us write p to the p equal to e to the minus k n by m, and minimizing a probability is the same as minimizing the log of that. So, let us take the log of the false positives, and the log of the false positive is nothing but this log of 1 minus p to the power k, because p was this expression and k comes. So, it becomes k log 1 minus p. Okay. So, and if you plug in the value of k using the definition of p, you get minus m by n log p log 1 minus p. Right. So, now it is really a simple question of calculus, right, but we are going to be even lazier. What we will say is, let us just plot this expression log p times log of 1 minus p minus log p times log of 1 minus p, and here is a plot I have generated using Wolfram alpha. It is very easy to see that this expression is minimized at the midpoint, that is at p equal to half. Okay. You should really take the derivative of this and set it to 0 and then check the second derivatives and so on, but I am just being lazy. So, this expression is minimized at p equal to half, which means that the optimal value of choosing p and therefore that of choosing k is really p equal to half, which means that k is m log 2 by n. So, here we are using the natural base for log. Okay. So, this optimal choice of k gives you a false positives, that is 2 to the minus m log 2 by n, and this you just get by plugging in the value. Okay. So, now if you want a false positive of delta, let us supposing you are a data science engineer and your manager has come to you and sort of and asked you to design a Bloom filter with a false positive rate of delta, right. Now, you know what to do, you get to choose k and you get to choose m, right. So, m, and you tell him that okay, I am going to need this much, I am going to need a machine that can hold this size of a bit array, and the size of m that you need is log 1 by delta times n divided by log square 2. So, all of this you just get by plugging in the value of k and by plugging in the value of m. So, for example, if you want 1% false positive rate, which is potentially fairly small, you only need 7 hash functions and a total of 10 n bits, right. So, now what we have is a data structure that has only constant times n number of bits, right. Remember, n is not the size of the universe, n is the number of elements that we want to store, right. And you need something like a constant times that for a small enough constant, and you need 7 hash functions. So, at query time you only need to calculate 7 hash functions of the query and you look these up. So, it is fairly fast. So, Bloom filters have widespread application whenever false positive rates are tolerable. In fact, a very celebrated use is was by this web browser Chrome. So, what did it do? It used to store a Bloom filter against for potentially malicious URLs. Okay. So, this Bloom filter, so suppose you type a URL in the browser, I mean in the Chrome browser, right. So, now the Chrome browser is going to give you a warning, it typically still does, to say that this URL is potentially malicious. Okay. So, how does it do that? Well, what it does is that it creates a Bloom filter of the malicious URLs that it has, and it ships to each of the clients. It ships to each, your machine has one of these, potentially has one of these Bloom filters. So, when you type this query, when you type this URL is checked against this client side Bloom filter. Now, if the client side Bloom filter says no, that this is not malicious, then you can just go ahead. But if the client side, because Bloom filters do not have false negatives, but if the client side Bloom filter says yes, this is potentially malicious, well, at that point Chrome sends this URL to the server and does an actual check, because because the probability of false positives is small, right, the number of times it is contacting the server, it decreases, right, it decreases beyond this naive solution if you were contacting the server with every potential URL, right. So, similarly, I mean it's used a lot in all these distributed databases such as Bigtable, HBase, Cassandra. What they have is that they have their data columns that are distributed over multiple machines. Okay. And now Cassandra, for instance, given a particular column, right. Suppose you are asking that does this machine contain the column, right. So rather than doing anything else, Cassandra first has a Bloom filter that it carries around and it tries to answer a yes no question using this Bloom filter. And if this Bloom filter says no, then that is it. But if the Bloom filter says yes, at that point Cassandra does some more computations in order to sort of do in order to decide whether to actually do a disk lookup for that particular column in this machine. It is also used in Bitcoin for wallet synchronization, but we will not go into the details of that. So all very nice, but there is one particular problem that you might already have noticed. What do we do if we wanted to delete an element, right? I never showed you what to do for deletion in Bloom filter, and it is not surprising that in Bloom filters you cannot delete. In ordinary Bloom filters you cannot delete, because once you delete, right, your analysis of our analysis of the optimal k goes away, because now although I mean you might have false negatives also, because although you have inserted an element, maybe you deleted one of the bits, you made one of the bits to be 0 when you deleted some other element, right. So therefore this is not obvious. A solution was given in terms of this counting Bloom filter, and it is very intuitive. What it says is that okay, previously each element of the Bloom filter used to contain a single bit. Let us now add to it a small counter. So think of it as follows, that we have the array, and now we have a small counter of let us say 4 bits with each position of the array. Okay. So now when we add an element, right, we will go to the counter and we will increment that particular counter, right. So for every I from 1 to k, we will go to the corresponding counter and increment it by 1. Now when we want to delete an element, again we will go to that counter, go to these corresponding counters and decrement these counters by 1. Okay. And these counters will be small, these counters will be like 4 bits per counter. Okay. So it is possible to show using analysis that is almost similar to that of Bloom filters, a little more complicated, that this is actually fine. Using 4 bits per counter is fine in most cases. False negatives can happen, but with very small probability, and false positives, the analysis of false positives is similar to that of Bloom filters. So, and there are a lot of other very interesting extensions for Bloom filters. Here is a very interesting question that we used for every input element that comes, we hashed it k times using k hash functions, right. Can we do with less hashing, much less hashing, maybe only with 2 hashes? It seems possible actually. A very interesting use case of Bloom filters is when you are, as we mentioned, is when it is used in the distributed setting. In that case, sometimes what happens is that you want to compress this Bloom filters and send it across, right. Because in the use case of Cassandra, if Cassandra was storing that okay, that this machine has these columns of the data and it creates a Bloom filter using that, it might want to store that machine, might want to send that Bloom filter to other machines after compression. It turns out that Bloom filters can be compressed very nicely. Furthermore, there are other structures that theoretically at least use less space, less randomness, and sometimes less memory lookups. However, most of these structures are really not very practical yet. They have been, I mean, they kind of work for ranges of error probabilities and the data size that are, I mean, for all practical purposes, Bloom filters, the performance of Bloom filters still beats the performance of these more theoretical structures. However, if you are interested in research, this is an excellent area to look into. And the primary reference for this lecture is the survey of Bloom filter by this excellent survey by Andre Broder and Michael Mitzenmacher, and some of the use cases and pictures were drawn from this particular blog site. There is also a very nice analysis of Bloom filters in the book Randomized Algorithms. So, that is it for today. Thank you.